All right, welcome everyone. Thank you for joining us. We're going to kick off the webinar today. My name is Sydney Gillette. I'm from the SPEL team as our MLOps Solutions Advisor. Thank you, Alexi, for hosting this today. For those of you who are not familiar, we are SPEL. And SPEL is a powerful MLOps platform for machine learning and deep learning. What does that mean? We are a platform that streamlines machine learning and deep learning experimentation and deployment. So we're an end-to-end machine learning platform, and our infrastructure and tools allow anyone to prepare, train, deploy, and manage machine learning projects. This is a webinar series, so if you're interested in joining our future ones, please visit our website, spell.ml, and at the bottom you can sign up for our newsletter, and that's where we will make announcements of future webinars. One quick thing to note, we are going to have a Q&A, so if you have any questions during the presentation, feel free to put them in the Q&A. We will be monitoring and getting to those at the end. And I will kick it off to Alexi, who is our developer advocate, and let him begin the presentation. Thank you.
All right, thanks, Sydney. Hello, welcome everyone to this webinar. So today we're going to be talking about a subject which I think it's very important. It's something that is implicit in a lot of machine learning projects, but doesn't often get as much attention as I think it really ought to get. And that's this problem of machine learning project scoping. Right? When you jump into a project, how do you make sure that the approach that you follow and that you use for dealing with some of the difficulties that come with working on projects in this space? How do you do that effectively? This talk is a collection of a bunch of tips and kind of tricks for helping to manage this workflow. A lot of them come from the data science consulting world, hence the subject matter of the talk, because data science consultants in particular run into this issue the most. How do we actually organize and leverage machine learning in an effective way in our projects? This talk is going to be split into two parts. The first part, we're going to talk about machine learning project scoping, what it is and why it's such a hard problem. And then in the second part, we're going to jump in and see a few different tips and tricks and techniques that can help you get things moving. All right, without further ado, let's jump right into it. All right, so project scoping. What does that even mean? Well, first I'm going to make a couple of observations. First observation I'm going to make here is that machine learning model development projects typically follow a pretty well-defined performance curve. For me, the best example I can draw to show what I mean by this, it comes from Kaggle. So Kaggle, if you're not familiar with it, is a machine learning competition firm. What Kaggle does, its kind of core competency, is that it organizes competitions where there's a task and there's hundreds, thousands of people who are all working on that task. Sometimes they're collaborating, sometimes they're competing, but they're all trying to, at the end of the competition, come out as the person or as the team who has the best and most performant model for solving for that task. So in this example, this chart showcases progress on a competition progress for a dark matter mapping, galaxy mapping competition that Kaggle hosted all the way back in 2012. On the x-axis here, you can see kind of the competition timeline. So all the way on the left, that's when the competition began. All the way on the right, that was the end of the competition. That was when the winners were announced. On the y-axis, you see the error, right? As people kept building better and better models, the error kept dropping more and more. Now, what's really interesting about this graph is, and the thing that it kind of showcases, which is really typical of all machine learning projects and all deep learning projects, is the shape of that improvement. You can kind of divide this graph into two parts. The first part, you have a lot of really large jumps in performance, right? They're getting in there, or you're working on your project, and you start with some baseline model, and then you start incorporating those kinds of really well-known techniques, which are going to work on this problem. They're going to have a really big effect. You start throwing batch normalization in there. You start using a more sophisticated learning scheduler, learning rate scheduler. You use a better optimization algorithm, et cetera, et cetera, et cetera. Whatever the bag of techniques you use, you start incorporating those techniques into your model. And as a result, your performance is going to go up. Your performance is going to go up precipitously, right? And your loss is going to go down very, very quickly. But you reach a point during the project when those easy wins are no longer possible. You reach a point where you've kind of exhausted all of the simple things that you can do. And now you're looking at kind of more complicated changes or more complex changes that you need to make to your model to win, to make much smaller gains in your overall performance. Towards the later ends of the competition, it's very typical to spend a lot of time developing new architectures or new ideas or new approaches, which only result in 1% improvement in performance or 0.5% improvement in performance. Very, very small numbers. With carrier competition in particular, can often go down as small as 0.1%. And this is extremely typical of machine learning projects in general. Every machine learning project is going to be shaped like this, right? You're going to be making a lot of really big improvements at the beginning when you're just moving from your baseline to something which is kind of close to the state of the art and kind of close to the best that you can build with the current technology. And then at the end of the project, you're going to be making much more complicated changes with much smaller amount of benefit. Another way of kind of presenting this from a flip perspective is in terms of like the cost, right? If I need to achieve a certain amount of accuracy in my model, how much is it going to cost me to do that? Well, if you only need, some not particularly impressive amount of accuracy, the amount of work that you need to do is fairly small. You can just use a heuristic, or you can just take a model, a pre-trained model off the rack pretty much, throw your data at it, and you're good. But as the scale of the accuracy that you need increases, the amount of work you have to do to actually achieve that accuracy increases superlinearly. It increases exponentially. If I need to achieve a certain metric, if I'm at a certain point, I need to achieve a certain other point, the actual amount of effort it's going to take for me to make that jump is going to be highly dependent on how close I am to the edge of that cost curve. Okay. Now that's our first observation, right? But the second observation, which is equally interesting, is that it's almost impossible to forecast in advance how difficult it is going to be to actually build one of these models. In 2014, I think the concept that best encapsulates why this is difficult is something called the case principle, which stands for changing anything changes everything. Case. So this is a principle that was presented in a very influential paper published by a bunch of Googlers all the way back in 2014. Titled "Hidden Technical Depth in Machine Learning Systems." You may have already read it because I think it's one of the most widely read papers in machine learning engineering. And basically, what this paper talks about, what it outlines, is this idea that because of how complex deep learning models are, and because of how, in many ways, opaque they are to us as kind of the modelers, the practitioners, the engineers, it's very easy to make very small changes in your data input or in your layers or any aspect of the model, which seem like they should have very small, if any, effect on the results your model generates. And you get to the end of the model training, and you see that actually it results in these wild swings in what's going on. All of a sudden, the model is predicting things very differently, or it has a very large drop in accuracy, or has a very large increase in accuracy, or the places where it's inaccurate have changed or switched places. This is it's just something that's kind of implicit in how deep learning works and how deep learning models work, is that it's just really difficult to look at a data set just with the naked eye and say, I know how long it's going to take for me to build a really effective model on this. And this is, I would posit that this is the primary source of complexity in many, even most deep learning systems today. If you look at deep learning systems in production, most of them in most of the cases, the actual model itself is only a very small, tiny component of the overall architecture. And most of the actual code is surrounding it. Is the logging and the monitoring and the alerting around, making sure that your model is actually doing what you think it should be doing. So I'm going to go ahead and illustrate that with a concrete example. Again, drawing from, from my experience at Kaggle and with Kaggle competitions in particular. So, Kaggle competitions, we had to put together, problems that our community had to solve. And, we had this particular problem, and actually skip over these slides because I think they're slightly distracting. We had this particular problem that, changing anything changes everything. And so as a result, we don't really know, you can look at benchmarks all day. You don't know how a model is actually going to perform on the actual data set that you have at hand. And this was a really big problem at Kaggle. And this kind of leads me into one of my favorite charts of all time. My favorite things to have learned during my time there. So if you look at this chart, let's take a minute to kind of analyze it. This is a plot of every competition that Kaggle has ever hosted. And it's plotted in a very particular way. On the bottom axis is the competition timeline. So, on 0, this is the beginning of the competition, when the competition started. And then 1, that's the end of the competition. The last day of the competition, that's when the results were revealed. And it was revealed who had in the end built the best model. On the y-axis, we have the scaled results, where 1.0 is the performance of the model that ultimately won the competition, and 0 was the performance of the benchmark that was provided at the very beginning of the competition. So, all the lines on this plot are broken up into quantiles. So every 10% of competitions rated by hardness. So the red line that you see there is the 10% hardest competitions that we had hosted on Kaggle. These are the 10% hardest problems and the problems that the community struggled with the most. The purple line at the very pink purplish line at the very top, that's the 10% easiest competitions. Those are the 10% of data problems and tasks that our community found the easiest to solve, and everything else is somewhere in between those two. Now, it was for the Kaggle competitions team, the goal was always to have something that was as close to this green line in the middle as possible, to have something that's as close to that 50th percentile as possible. As for the Kaggle competitions team, what makes a good Kaggle competition is that there's a little bit of time for those kinds of small optimizations at the end of the competition, but the bulk of the competition should be spent making those kinds of fundamental advances. Changing a different trying out a new architecture and finding that it results in a 5% improvement in your model accuracy, and being very happy about that. Competitions team did not want people to be spending a week or more doing things that would result in only like a 0.1 or a 0.5 improvement in the overall accuracy. So the green line was ideal. And the competition team is very experienced group of folks. I mean, the Kaggle has been hosting competitions for almost a decade at this point. And even still, it was really, really hard and really, really challenging to actually organize competitions that, to set up these projects for folks where the timeline was exactly right. If you look at the red line, you can see an example that for a competition that we did not give enough time to, right? And so there was never, people were still making fundamental advances at the end of the competition. And if this competition had been extended, it seems very likely that people would have found a significantly better model. On the other hand, the pinkish purplish line at the very top, that's an example of a competition that ran for too long. The community found all the fundamental things that they needed to build to address the problem too early in the competition, and as a result, they spent too much time, almost the entire second half of the competition, just making really small hyper optimizations. So this is something which is particular to Kaggle, right? Kaggle is one of not very many companies that organize these competitions, but machine learning projects that you work on at your organization, the projects that you work on your own time are not any different, right? Kaggle has a ton of experience organizing these projects, and they found it really, really difficult to actually organize it successfully. They find it really, really difficult to get the timeline just right. This is and this is a challenge that I think is entirely it speaks very much to the difficulties of knowing how long something is going to take when deep learning is involved. All right. So kind of in conclusion, I think that if you are familiar, with software engineering management, you know that project scoping is a really hard problem in software engineering. And even still, it's an even harder problem in machine learning. It's a harder problem because in software engineering, just the way computers work, you have one input or many inputs, and you have one output or many outputs. And based on what inputs you put in, what your outputs are going to look like. You can test that. You have contracts that you can write that describe the performance and the behavior of the software. In machine learning, you don't really have that. You have a data that you don't really always fully understand that's going into a complicated model that you don't really fully understand what it's doing, and it's coming out and giving you predictions, which can be difficult to trace all the way back to the source. And that makes scoping machine learning projects involving deep learning really, really challenging. So now that we've outlined some of the challenges of deep learning project management with these kinds of projects, let's jump into some of the things that you can do. Now, like I said, a lot of these things are going to come from the data science consulting world, because data science consultants, they have to come into organizations using data that they're completely unfamiliar with and figure out how to effectively leverage that data in order to produce insights or to produce models which actually do something useful. So they run into this problem of scoping, of understanding what you can actually do with the data that you have, more so than almost anyone else out there. And so I think that the techniques that data science consultants kind of have written about are the most interesting ones to think about, because they're lightweight. They don't, you're not creating so much process that you're getting in the way of actually doing the deep learning, but they're extremely useful because they keep you from stepping on landmines. And throughout the presentation, I'll give a few examples of some of the problems that this lets you avoid. There are 5 tips in total. So first one is to separate your project into explore and implement phases. So when you're doing a deep learning project, one thing you typically need to do is is to have kind of a proof of concept period at the beginning of the project, right? If possible, you want to agree kind of ahead of time of some performance benchmarks or some performance metrics that you think like a really, really simple, really dead simple model ought to be able to achieve. And then you just kind of go out there and you like implement like a super basic unit or a super basic convolutional network, a super basic ResNet, whatever the case may be, on the data, and see what you get as a result. Make sure that what you get when you pass the data through these basic benchmark models actually aligns with what you expect them to be able to do. Okay. The reason this is important is because, again, you're never going to like know the data so well that you're going to know every single problem in the data right away, right? And you can there's a lot of great techniques out there that people are publishing about all the time and every day. But a lot of those things, if you're familiar with how academia works, you know that a lot of the things that people publish are not necessarily extensible to the problem you're facing right now. So when you approach a new project, you want to like make sure that the techniques are actually extendable, and you want to make sure that there aren't any nuances in the data or problems in the way the data is collected or built or designed that are so overwhelming that they invalidate your ability to perform the project in the first place. And I can actually give a very specific example of a case where this actually occurred. My last company I worked for was a startup called Quilt Data, and one of our users or one of the companies we were talking to was a sports analytics company, and they had a really interesting product where they basically took video data of athletes, doing sports things, hitting a tennis ball or batting or catching a football, and they would apply deep learning to the video in order to get kind of data about what was going on that could then be summarized and aggregated and turned into a product that was useful for kind of coaches to use as part of their training regimen. And they were running into a lot of issues with their model. Their core line of business model was not performing as well as it should be, or as well as they thought it ought to be able to. And they kept throwing like new techniques at it and new ideas at it, and they did a lot of work, making the model more sophisticated. But they still could not seem to like crack the nut. It was unclear why it was not performing the way it was supposed to. And so one day, almost, and they honestly almost got to the point where they considered canceling the project. And so one day they kind of took a really hard look at the data they were using, and they discovered that one of the vendors that they were using for their data sets had some issues, some errors that are creeping into the data that they were using that was not obvious at first glance. It was something that was really kind of nuanced. Once they found that issue and they corrected it, they found that their performance jumped up wildly. There's a huge improvement in performance. All of a sudden, they had gone from something that was underperforming their expectations to something that was overperforming their expectations. Well, what had changed? Well, the only thing that had changed is that is the data that they were using. Changing anything changes everything. The whole idea of having these two different phases in your project, it's really simple. It's a really simple thing to do, really simple to implement. You can say, I'm going to need 20 hours or 40 hours at the beginning to just sit down, get some benchmarks up on the data, see what I see. And it kind of protects you from getting too far ahead of yourself, right? In this way, it kind of protects you from making assumptions about the cleanliness of the data that you have, that are not actually true in practice, or making assumptions about the extensibility of the techniques that you're going to use that do not actually perform on the data that you have. That's the first tip, and it's a really good one, I think. The second tip is to collect human and model performance benchmarks on your data set. So what does this mean? I mean in particular, not like state-of-the-art performance benchmarks on this task for academic data sets. I don't think if you're building a image classifier, you don't actually want. I mean, it's not as informative to know what the state-of-the-art performance for classification on ImageNet is, as it is to know what the performance of the same models is on your actual data set. Again, don't assume that something that's going to work for this academic an index data set is actually going to work for the data that you have right now in front of you in practice, the things that you're going to actually feed to the model. So kind of going into the same idea of having this prototyping phase in your project, is this idea that you really ought to, before you get too far into it, collect these kinds of benchmarks on your data set. Now, if you want model benchmarks, the really great resource is Papers with Code. They recently did a pretty huge update, which made them even more useful. It's a great website, and I definitely recommend checking it out. And what you can do is you can just go on there. You can search for the task that you're trying to do, whether it be classification or sentiment analysis or whatever the case may be. Pull up some models, throw your data at those models, and see the result that they get, and see whether or not those results align with your expectations. There's also human benchmarks, right? I think the story I like to tell about the usefulness of human benchmarks is something Andrew Karpathy did way back in 2014, where he sat down and he personally competed with ImageNet. He competed with Google Net, I believe it was called, on the ImageNet dataset. Why did he do that? Well, he did it because he wanted to get a personal sense of what were the challenging things to do in the data set, and where were the areas that the current state-of-the-art neural network models, like what were the areas they were struggling with. By kind of sitting down and classifying 1,500 images himself, you don't need to go that far. He was just doing it because he was doing it in part because he wanted to write a paper about it. But by sitting down and going through that process himself, kind of physically, that kind of gave him a lot of intuition about the things that the model was doing really good on, and also the things that it was doing really bad on. It let him really see where is it that my model is struggling, and where is it they could potentially improve it. And I'm not going to go into too much detail here on what exactly he found, because if you're interested, you should definitely check out the blog post. But I'll say that there were some interesting things. It was Instagram filters were a problem. abstract representations of image content was a problem. Kind of a lot of really interesting things that came out of that experiment. I really do think that it's oftentimes very useful to, with a wide variety of tasks, to actually sit down and do it yourself, even a little bit, because that gives you some intuition about like, first of all, what is the benchmark of human performance on this problem, and also what are the issues in my data set that are going to be a challenge later on down the road. Okay. Third tip is negotiate performance benchmarks with stakeholders ahead of time. So, you're not building a network for fun typically, right? Like if you're in a production setting, you're building a network because you have some value that you're trying to drive, some value to the business that you're trying to create by putting a neural network or deep learning model or machine learning model into production and doing some task. That's fundamentally a business process, right? And because it's a fundamentally business process, it's really useful to kind of negotiate ahead of time what is the performance that the model needs to have, right? What constitutes good enough? What's like great performance? What's fantastic performance, right? Like you want to find what these breakpoints are, so that you can kind of use them to meaningfully communicate with your non-technical stakeholders in the project. They also allow you to do something else, which is very useful when you're managing a machine learning project, which is to kind of assess, when you reach a certain point in the project, assess whether or not it's worth continuing it, right? Because like I said, performance is oftentimes something that's hard to get. So when you get to a break point, you get to a point where the model is quote unquote good enough for something, it's useful to kind of step back for a moment and ask yourself, how much work do I expect it to take for me to get to the next breakpoint? How much work do I expect it to take me to improve the performance of the model so much that it changes the way that the model actually gets used in practice by the business? If the answer is, too long, up to whatever your approximation of this idea of too long is, then maybe it's not worth doing that. Maybe that's the point where you perform your final hyperparameter searches, clean up your code base, and deliver the project in, and move on to the next thing that you can do at your organization. Regardless of which choice you make, I think it's very useful and very important to at least have that conversation with yourself. Tip number 4 is to keep updating your time cost estimate as you proceed. So as you go through the motions of a deep learning project, of a modeling project, you're going to get more and more accurate in terms of your understanding of how hard the problem is, right? When you're at the very beginning of the problem, you have no familiarity with the data set. You only have some familiarity with the techniques, but you don't really know anything, right? You're not in the weeds. You haven't spent time building this model yet, and so you don't actually have a very good estimate for how long it's going to take, right? Again, engineering scoping, time scoping is already really hard. Machine learning, it gets another degree harder, and that business people tend not to like that. Business people are all about time estimates and cost estimates. They want you to know concretely, how much risk is there in performing this activity, and how long is it going to take, and how much money is it going to cost us, and where do we build things, and how do we handle this whole process? So telling a business stakeholders, or a line of business stakeholders, that I don't really know how long this is going to take, but pay me, is kind of hard to do. So one thing that you can do to ameliorate this problem is to kind of keep updating your estimate of how long the project is going to take as you go through the project, right? When you're at the beginning of the project, you'll have some relatively rough, maybe it'll take 80 to 100. It'll take me, I don't know, 80 to 240 hours or something, some crazy variance like that. As you're stepping through the project, you build more models, get closer and closer to that state-of-the-art performance. You have a better estimate of how long it's going to take, and you're going to be able to squeeze that time down, right? You'll be able to say oh, I think it's going to take me 100 hours total, give or take, right? That is when you're actually engaged in a in a deep learning project that is a really useful thing to be able to do and a really useful thing to be able to say. Like here's a more exact estimate of how long I think this is going to take me. Okay, how's that? 4 tips so far. Let's move on to just the last one. All right, last tip of the day is to have a library or a zoo, whatever verbiage you're comfortable with or familiar with or want to use, of well optimized models that you're comfortable using. What I mean by that is that when you get into doing a deep learning project, it's very useful to have prior models that do similar things that you are familiar with because you've worked with them in the past. This is advice that was given to me by a guy named Vladimir Iglovikov, who is a grandmaster on Kaggle. And this is actually something he used, something he did that was very effective to jumpstarting his career. He was a grandmaster on Kaggle. He competed in a lot of competitions. He had a lot of models that he built during those competitions that he was very familiar with. He was very comfortable using them because he knew them so well. And so he had kind of a very refined understanding of kind of a variety of different techniques. And he was able to use that. He now works as a deep learning engineer at Lyft on their autonomous vehicles and whatnot. And he kind of talks about how when you run into a new technique or a new paper, or you're exposed to a new idea of something that you can do in deep learning, or something you can do with your models, something that you can do with your data, it's really helpful to have just kind of models that you've built just lying around, because you can just instead of grabbing like the super optimized, really complicated model that you're working on day to day, you can grab one of these simpler models that you're familiar with and throw the technique at one of those and train that model and see how well it does, see how well it performs. Maybe if it works well, again, don't trust what's written in the paper. If it works well, it's worth investigating. It's worth investing the time investigating that technique for your production facing applications. But if it doesn't work, if it doesn't seem to work in that case, why would you expect it to work with your production data? Because this is, I think, a technique which is really really handy. Once you have a lot of experience in the field, having that experience really helps you to kind of jumpstart further future projects really effectively. All right, so that about rounds out the presentation. So to summarize, we talked about project scoping and machine learning. We talked about how project scoping is kind of this difficult problem in software engineering, which gets even harder when you're dealing with deep learning and with neural nets. I kind of presented my own case for what I consider to be kind of the best summarization of this issue. The experience of Kaggle competitions and how hard it is to get like a really good project timeline assigned to them. And then we looked at 5 different techniques, most of them taken from the data science consulting world, that are really useful when you're actually engaged in a deep learning project and actually doing things in your business that are production facing and building things out. So I hope that you found this useful and entertaining. Here's a picture of one of our coworkers' beloved cat and my Twitter handle. Now, I believe we have some time for questions. Okay. All right, let me just check this here really quickly. Okay, our first question. Is there any guidance on how much time should be spent on exploration versus implementation? Yeah, that's a really good question. So it depends, right? That's such a cop-out answer, but the reality is that yes, yeah, it really depends. Like, because I'm saying, we're saying project, right? But oftentimes a project isn't as simple as I'm going to build a model and I'm going to train it from point A to B. Oftentimes it's, I want to try out I want to, see if I can apply this new technique to an existing model that we already have in production, or to do any other kind of smaller optimizations. The amount of time that you should spend in this exploratory phase of the project, it depends on how much time you're going to end up spending actually implementing it in production. and how confident you are that the research you're going to do before you actually go ahead and start throwing at your production model is actually going to extend to what you're doing in production. If you have some stuff, which if you have something that looks really, really promising, who knows, maybe you can just chuck it into your production model right away. But if you have something that you're a bit more skeptical of, but still want to try out, then it might be worth spending more time exploring it before actually jumping into it. Okay. What would you say is more important? Really good question, by the way. What would you say is more important, model accuracy or model performance? Um, Good question. So accuracy is just is a single specific performance metric, right? When you're actually building deep learning models in production, model performance, model accuracy, all of these metrics that, the loss metrics you're actually going to attach to your model, those are only as useful as they are connected to the actual business processes, right? Again, like we're talking about, like retention, we're talking about, relevance to users, we're talking about all these kinds of real world effects that your model is trying to have. So the most important thing really isn't model accuracy or model performance. It's choosing, measuring your model performance using metrics which are connected to what's actually happening in the real world, right? If I am, doing a shopping basket, if I have a model that is predicting user shopping baskets, for example, or the kinds of products I think that they're going to buy, the metrics I really care about are the ones that get me closer to finding the things which are relevant. Okay. What's the best way? The next question. What's the best way, do you think, to manage your model zoo or library? Yeah, it's an interesting question. So I don't think there's like a best method per se. Ultimately, you should use what you're comfortable with. And in my experience, every data scientist I talk to is comfortable with like a different kind of thing. Like if you have seen Jeremy Howard's Pass the Eye course, you'll see that he really likes having kind of an index of academic papers with like tons of like notes and footnotes and like connections to things he's built, kind of written into there. And that's basically how he like indexes his his models, right? Is he has a paper that he gets excited about, he marks it up, he builds kind of like some model that's kind of attached to it. He has got a code repo, and then later on when he wants to find that code again, he kind of like he kind of goes through that go through his paper annotations to get it. Personally, I like Colab, I like Kaggle. I think both of these, the fact that both these products offer free compute is very useful for just putting together these again index models, right? Things that you've built. You don't even need to be able to run them on these sites anymore. You can just kind of put them up. And of course, for really complicated projects, GitHub is like the way to go. So I wouldn't say that there's any one ring to rule them all. Right now, everyone's workflow is a little bit different, and it's talk to your friends and see what they do and see what works for you. All right, I think our last question so far of the day so far. Okay, all models degrade over time. How do you ensure business stakeholders understand that ML projects are never done and need care and feeding, i.e. retraining? Excellent question. All right, so how do you do it? Well, that is the problem, isn't it? How do you do it? How do you do it? I don't know. This is part of the kind of the communications that you have to do when you're doing developing on a project, right? This is absolutely right? You can kind of hand off. You can build a website and hand it off, and you can expect that website to just run in place for a very long time and never have any problems. When you build a deep learning model and deliver a deep learning model, the state of the art changes. Or there's some feedback loops in what the users are doing, or user behaviors change and the fundamental assumptions of the model no longer hold, right? Every single company that uses deep learning in production, they have some kind of retraining loop involved in their production models. It depends how often they retrain, depends on the company, right? Netflix because of the cold start problem, Netflix retrains as often as they can. So we retrain their models, their user recommendation models every day, several times a day. If you run an e-commerce store, you can probably get away with only retraining your models every couple of months or so. In terms of convincing managers that this is something that they need to invest in, I think what's helpful is to point to what's always helpful is to kind of draw examples from best practices, right? You can point to what other companies are doing. You can talk about what this problem is and why it exists, and show here's what Netflix is doing. You should give them an excerpt of the machine learning engineering of some machine learning engineering books talk about this problem and talk about how big of a problem it is. Unfortunately, again, this is a human thing, right? So much of software isn't writing code or managing code; it's managing humans. So that's just something that's just something that you kind of have to figure out. And it's going to depend how difficult it's going to be. It's going to depend on the organization you work for. All right, I think that's all the questions we have so far. I think that's going to just about wrap up this webinar. If you have any other questions, feel free to shoot me a tweet. I'm at Resident Mario on Twitter. And let's get to wrap up. All right. Okay. Thank you, everyone, for coming to the webinar. As Sydney mentioned at the beginning of this talk, we have a newsletter, ML Ops newsletter that we run. We'd love for you to sign up. If you found this content of this talk interesting, you can go to our website at www.spell.ml and navigate to the bottom, and we have a little sign up that you can click on to get that done. And if you enjoyed this webinar, you'll be happy to know that this is something that we're hoping to start running on a regular basis. So, follow us via our newsletter or follow us on Twitter to hear more about what we're doing. This has been Alexi, and I hope you all enjoyed this presentation. Thank you.